All right, for you AP folks, this is questions 6 through 12. The first one's define Galileo's law of falling bodies. The thing to remember there is really not just defining something, but that fundamental concept or idea that he came up with where acceleration for something in free fall in the absence of air resistance is not dependent on anything's weight. So whether you're dropping a feather or a hammer or your car, they all would be neck and neck, right next to each other if air resistance is negligible. Right? That's Galileo's law of falling bodies. More importantly, I suppose, to be able to use that and apply that, he found out that things falling, the distance it falls is proportional to the time squared. So the distance it falls, like in the first second, all right, would be 1 distance unit, and then the second would be 3 distance units for a total of 4 distance units. Now these questions here talk about throwing something up in the air. So, but remember, anything that has uniform acceleration, whether it's speeding up or slowing down, and whether it's in the air or moving horizontally, like something skidding to a stop or whatever, distance traveled is proportional to the time squared. Whether you use a delta x or an h or a d, the distance traveled is proportional to the time squared. For uniform acceleration, which is what we're talking about here, the distance traveled is proportional to how fast the object's going squared, all right? Whether it's speeding up or slowing down uniformly, all right? If you're going twice as fast and then you're going to slow down to a stop, you're going to go 4 times further. Twice squared, 2 squared is 4. If you're going twice as fast, you're going to slow down to a stop. You travel 4 times further than the original velocity v. If you're speeding up from 0 to v, then you compare that to speeding up. How far would you have to go with the same acceleration from 0 to twice v? Well, it's speed squared, so square 2, and you get 4 times further. Distance is proportional to the speed squared. And all of these things are assuming that the acceleration is the same number. It's not changing. Okay, so these questions ask what would the velocity vector, this is the one where Wanda stands outside and throws the ball straight up in the air. It leaves her hand with an initial speed v, comes to a stop at its highest point h, and in time t, ignore air resistance. What would be the velocity and acceleration values at the apex, at the highest point? Well, at the highest point, of course, it will have stopped, so the velocity would be 0. But the acceleration would still be negative g, negative 9.8 or negative 10, negative g. If we make upwards positive, then what would be the sign of the displacement, velocity, and acceleration of the ball on the way up? Well, of course, it's on the way up. Displacement's positive and velocity is positive, but your acceleration vector is negative, right, because it's negative g. At the top, of course, we already said that velocity is 0, but the acceleration is negative g. What would be the sign of the displacement, velocity, and acceleration of the ball on its way down? Well, as it's displacing down, that's a negative displacement. That's a negative velocity and a negative acceleration. If you had thrown the ball from, if your displacement measurements are from the ground and it's gone up and now it's on its way down, it still has positive displacement with negative velocity, negative acceleration, because it's above its original position, even though it's on its way down, if you measure it from down here. It depends where you're measuring from. Of course, if you're just measuring from the apex and just looking at the trip down, then it's falling, negative displacement, negative velocity, negative acceleration. If you're measuring it from the very bottom, where you originally threw the ball, and then even though it's already finished its upward motion, it's on its way down, it's still above its original position, so that's why it's positive displacement at that moment. It's a positive position change, which is getting less and less as it falls. Right? Negative velocity, negative acceleration on the way down. Okay, how high has the ball risen after only half the time t has elapsed? Support your answer. Remember that, as I was saying, distance with uniform acceleration, distance is proportional to time squared. Okay, a half squared is 1/4. And in this case, if you're throwing something up, this is a great visual to remember. All right, it's going to travel less distance in the slower time. It's slowing down. So the second half of the journey on the way up is the slower one. It's going to travel less distance, right? Not travel as far. The same thing when you drop it. The first half of the journey is when it's traveling slower. It's going to travel the shorter distance. So just remember this, that you got 0 and t and a half, all right? The lower portion is always going to be the 3/4 of the motion. The higher portion is going to always be 1/4 of the motion. So if you throw something up in the first half of the moment, at the first half of the journey, first half of the time that's elapsed, it goes 3/4 of the journey, and then the second half of the time where it's traveling slower, it goes the other quarter of the distance. If you were to drop it, the exact reverse. As it's speeding up here, it goes 1/4 of the distance in the first half, and then 3/4 the other half. But it's always going to have that 1 and 3 ratio, again, because distance is proportional to time squared, you know, and like it comes out to be, you know, 2 squared is 4, all that stuff. So just if you could remember that visual, and again, that works horizontally too. It works horizontally also. What's the next one? How high would the ball go if she were to throw it with twice the original speed? That's over here, speed, distance something travels, whether it's height or you speeding up in your car or slowing down in your car. Distance proportional to speed squared. So if it takes a certain distance when you're traveling at a certain speed v, and then you double the speed and square it, so the double squared is 4, so the distance would be 4 times greater. Remember I talked about the car skidding to a stop and leaving tread marks, and if you're going twice as fast, you need 4 times the distance to stop. All right. If you throw something up in the air with twice the speed, it's going to go 4 times higher. If you're skidding in your car, if you're traveling in your car and you're going 3 times faster than some original speed v, 3 times faster squared is 9 times the distance required to stop your car. If you throw something up with 3 times the original speed, it will go 9 times higher. Distance is proportional to speed squared. Okay. The last one, notice that velocity is directly proportional to time. Speed is directly proportional to time, not time squared. There's no squared here. This is for the acceleration being constant. So it says, how much time would it take the ball to reach its highest point if Wanda were to throw the ball with twice the original speed? All right. If you double the speed, it's going to take, it's going to go a lot higher, right? But you double the speed to come to a stop, it's going to take twice the time. All right. Time and speed are directly proportional to each other for a uniform constant acceleration. So you double the speed, you double the time required. Okay, the same thing if you drop something. How much time would be required for it to speed up at the same rate of acceleration to get to twice its original speed? Twice as long, because especially if you drop it from rest and you want to get to 2v, you're going to need 2t. All right, if you want to get to 3v, you need 3t. Okay, the same relationships in terms of that are going to be going to show up whether it's speeding up or slowing down in terms of speed and time, distance and speed, and height and time, or distance and time. Okay, I hope that helps. I think that's everything. How much time? Yeah, I think so. Okay, so supporting your answer, I just refer to these things, and if you can remember these things, you'll be in pretty good shape. All right, bye.